Hello, my name is Leonardo Sacht, and my co-author Leonardo Souto Ferreira and I are going to present a work bounded by harmonic blending of Möbius transformations for flexible omnidirectional image rectification. Our method takes as input omnidirectional images, which are images that contain a whole sphere around a given point. Their 360-degree field of view guarantees that all information visible from the viewpoint is in the image. On the other hand, straight lines in the world appear bent. We propose a method that rectifies straight lines in these images while preserving their full spherical field of view. Before we discuss our method, let's take a look on previous alternatives and their pros and cons. The well-known perspective projection is able to rectify all lines in the scene, but causes too much stretching when the field of view is wider than 90 degrees, such as in this example. On the other hand, Möbius transformations are defined for the full spherical field of view and are conformal, but they cannot rectify all lines in the scene. The possibility of calculating Möbius transformations by specifying new positions of 3 points makes it possible to rectify one line, but not all of them with a single Möbius transformation. Instead of using one transformation, previous methods propose to combine multiple transformations using a technique known as linear blend skinning. In our context, this means mapping a point on the sphere given by its longitude-latitude coordinates lambda phi to a new position given by a weighted combination of transformations Tj that affect more areas where the associated weights are higher. For example, if we want to apply a specific transformation T1 to the area inside the circle without affecting other areas, we set the weight function W1 to be closer to 1 inside the circle and 0 far from it. Doing the same for other regions such as this green circle ensures that each transformation will only affect areas where their associated weights are higher. This approach was taken by Souto, Ferreira and colleagues in 2017 when they proposed to use Gaussian weights and Möbius transformations to rectify lines in omnidirectional images and obtain other effects in these images. Each set of 3 points in this figure will be mapped to new positions by Möbius transformations, and the transformations will only affect the regions given by these ellipses, where the associated weights are higher. This result from their method is successful at rectifying lines and performing local zoom on the central building. But this happens because the areas affected by each transformation are not so close to each other. In this case, where regions of interest overlap, the collinearization of groups of 3 points leads to this bad result, caused by the combined effect of different transformations in areas of overlap. We emphasize that this problem with their method always happens for indoor scenes, where lines in the scene meet at endpoints, making this method useful only for outdoor scenes. Another class of methods tries to find new positions for a grid on the sphere in a way to minimize distortions. Though they can produce very good results in a variety of scenarios, they are not designed to be applied to the full spherical field of view. We propose a method that overcomes the limitations presented by previous methods. It is able to rectify lines specified by the user in an interface. It takes as input an omnidirectional image of the full spherical field of view and outputs a result with the same field of view. And it offers an intuitive interface that allows the user to not only specify lines that appear here in red, but also to specify bidimensional regions as the ones inside the white polygons that were specified to prevent the final warping from affecting areas near the poles of the sphere. The output of our method shows how it is able to deal with very close lines without distorting other regions while preserving the full spherical field of view. This flexibility is explained by the formula that defines the inverse warping of our method. It combines the effect of multiple Möbius transformations Mj associated to each line using weights Wj that are optimally determined to be smooth and to affect only areas close to them. Möbius transformations are conformal mappings from the sphere to the sphere, being the natural tool to achieve outputs of the full spherical field of view with low conformal distortion. Originally formulated as mappings on the complex plane, they are uniquely defined by new positions of 3 points. In this example, a unique Möbius transformation maps Z1 to W1, Z2 to W2, and Z3 to W3. The correspondence between the sphere and the complex plane established by the stereographic projection defines a corresponding unique Möbius transformation on the sphere. The transformations are specified in our interface using bone, point, and cage handles. To each type of handle, we associate 3 meaningful points that will define a corresponding Möbius transformation. For line segments, the central point is said to be collinear to the endpoints. To every point handle, we define 2 adjacent points, and the position specified for these 3 points in their interface define their associated transformation. Point handles are especially useful to define local rotations, scalings, and translations. For cage handles, we treat each of their vertices as point handles and linearly interpolate their weights over the cage edges. With all Möbius transformations Mj specified, what is left to define are the weights Wj that will combine them into a single result. We use the bounded biharmonic weights, since their locality and smoothness ensure that each Möbius transformation will only affect the area close to its handle, and that there will be no noticeable transitions in areas affected by different transformations. Here we show an example of a badly aligned input image, over which we define point handles to locally rotate different regions to correct its alignment. On the insets, we can see plots of the 3 weight functions, which have higher values closer to the point handles and are smooth.
Sometimes, rectification of several lines leads to conflicting positioning of them. Takes example the following lines. Rectifying those lines independently leads to overlap, and the final transformation generates a bad result. To overcome this problem, we define an energy equation to find new final position of the handles in a way to preserve the relative distance between them, while enforcing line rectification as a soft constraint. Since we define the relative position using segmentation of the lines, the energy can be written in terms of equirectangular distance, and therefore it is minimized by solving a linear system of equations. This then leads to a fast implementation. This methodology leads to a much more natural line rectification, as we can see in this result using the relative distance preservation. Since the bounded biharmonic weights are defined in terms of minimization of Laplacian energy, we can speed up their computation by constructing our mesh using successive subdivisions of the icosahedron based on the position of the handles. This leads to a finer mesh around the most important regions of the image, without creating acute triangles that are bad for numerical computation. Our methodology was implemented in MATLAB, and the interface was developed with the guides toolbox. The program is divided into 2 windows. The first window is where the user defines the handles that will act as boundary conditions for the bounded biharmonic weights computation. To deal with bone handle intersections, we simply break them at the point of intersection, generating 4 bones instead of 2. We also use a clustering algorithm to couple spherical bones if the endpoints are below some distance threshold. In the second window, the user defines the Möbius transformation associated to each handle by moving the control points over the image. We also provide a button that rectifies all lines at once, which solves the linear system discussed before. If it's not desired to rectify all of them, we provide another button that rectifies only the segment selected by the user. We use the MATLAB implementation of the bounded biharmonic weights integrated with Mosaic. The average time per handle is 0.4 seconds in our standard resolution of 2048 by 1024 pixels. As we can see in the table, the majority of the execution time is spent in the weight computation and the transformation blending, taking approximately 70 and 23% of the time, respectively. The timing in these parts could be improved by a C++ implementation with GPU interpolation, and we plan to approach this task in future work. The other steps of our method include the optimal handles computation and adaptive mesh construction, both taking 3% of the time, and final image interpolation with 1% of time, and the Möbius transformation coefficients that take negligible time to be computed. Using the versatility of the bounded biharmonic weights, we can define regions that should not move using spherical cages. In this example, the regions desired to be preserved are the middle one, where the statue and windows should be fixed, and also the floor and ceiling of the building, while we rectify some doors and parts of the walls. On the left, we show the result without using the spherical cages. Note that while it accomplishes the desired line rectification, the unprotected regions got highly distorted. Notice, for example, the statue and windows. On the other hand, on the right, we use the cages previously mentioned, and the result is much better. The rectification of the lines is accomplished without badly affecting the other regions of the image. The use of Möbius transformations also allows us to define spherical zoom that does not lose information of the image, something that could happen with a simple linear transformation. In this example, you can zoom in the red car, allowing us to read the plate without losing sight of the rest of the area, but can be useful for surveillance applications. We can compare our methodology to the one developed by Souto, Ferreira and colleagues in 2017 in this very complex setting, with a considerable number of lines to be rectified. On the left, we see their result. Although their method rectifies most parts of the lines, their extremities are distorted due to the overlapping of transformation that occur in these areas, as shown in the left inset. Also, Gaussian or rectangular regions are not versatile enough to handle lines with such proximity. On the other hand, our method generates weights in a way that the transformations do not overlap, and the transition between transformations is smooth enough to be able to rectify lines that share endpoints. Additionally, the combined use of cages and vertical lines allow us to preserve good regions of the image, such as the person in the middle. We can compare our methodology to the one by Carroll and colleagues in this outdoor setting, with the aim of rectifying most of the lines of the image. On the left, we have the result by Carroll and colleagues. While their method is able to correctly rectify the selected lines, it's not developed to preserve the entire field of view. On the other hand, our methodology, on the right, is specifically developed to preserve the complete spherical view while rectifying the lines as well as the former method. Our methodology has some limitations. If the line aimed to be rectified is too wide, near 180 degrees, Möbius transformations fail to reach the expected rectification effect. Also, if an important line is not specified, it can be transformed in an unpleasant way. Our methodology does not guarantee bijectivity. Since the weights are calculated based on final positions of the handles, we can have effects such as the one in this image, where the regions inside the rectangle was most affected by the transformation of the point in the sun, and the external region was affected by the cage identity transformation, therefore creating two suns. To emphasize that this is an artificial setting and none of the practical examples had this behavior. Leonardo Souto thanks CAPS and CNPq, and Leonardo Sacht thanks CNPq for the financial support. The authors thank the Flickr Creative Commons community for making available their omnidirectional images. We made available our code and results in the following link. Thank you for watching.